Welcome to episode 20, season 3 of the Cosmic Pie podcast. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live on the campus of the University of North Dakota here in Grand Forks, North Dakota.
Yep.
How's it going, Robert?
It's been a summer so far.
Yeah. It's better than the last podcast that we did.
Oh, yeah. I mean, so far we don't seem to be having much in the way of technical issues. We'll see if that holds.
Now, we did a lot of changes, right, supposedly?
Yep. There was an update to the system. It seems to have cleared up most of the issues.
So we went from, Windows 10 to Windows 11 or something?
Something like that.
Yeah. So the IT people have been working with our computers, so we thank them for fixing things, because we definitely needed them. So hopefully that will result in not having any technical difficulties for the next 20 years, but I kind of doubt it.
I kind of doubt it.
Now, if you have any questions throughout today's podcast, feel free to use the chat feature that we have running. So you have any questions or comments you'd like to make, we'll go through that. And of course, we prefer if you keep those comments directed to the subject matter at hand.
Right.
Now, as a disclaimer, Robert, what do you think? Do you want to try this one?
Okay, we'll try this one. The opinions and all that expressed are those of myself and Wayne. They are not the opinions or the what do you call it? The official stance of the university, the Department of Physics and Astrophysics, University of North Dakota, so forth. You'll have to come at us.
Blah, 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 right?
Right.
That's the...
It's
We've
us.
heard that before, that term, right? Blah, 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 in a
Blah,
different
blah,
context.
blah.
You remember?
Yada, yada, yada.
Yeah, we won't get into that, but anyways. We are also on Spotify, Robert. Do you realize that?
No, I did not know that.
We are on Spotify, so you prefer to get your podcasts, your pods from Spotify. Feel free to go there.
Yeah.
The other thing, too, is we're also on Instagram. We should mention that.
Okay.
So if you plug in the Cosmic Pie _UND, you'll find us on Instagram. We now have over 1,000 followers. I'm very happy. It took a while to build up that, but we're there.
Woohoo.
So the next goal is to get to 2,000 followers.
Oh, 1,100? Oh.
No. We're going up by 1,000.
Okay.
It's inflation, you know. How are those tariffs working for you? You see how that works?
I'm still waiting to see on that one, but
yesterday was a big day in astronomy. Robert.
It was huge.
It was a huge day. Now, as a sort of a special disclaimer, I should note that I am part of the science collaboration for the LSST.
Okay.
So I have all the back information of what's been going on.
Okay.
So, but even if I wasn't involved at all, I still would plug this. Mm-hmm. And that, if you like, you want to go to our first slides, I guess, so people know what we're talking about. This is a telescope. It's 8.4 meters in diameter, the primary mirror. And we'll get to a slide a little bit later on that kind of illustrates in a little bit more detail how it functions as a telescope. Not quite the standard telescope that we're all used to if you're into telescopes.
Yeah, I've got some questions about it.
Yeah, it's a little different. So, obviously, a lot of money to build this telescope. It's located in Chile, near the Cerro Tololo, so the Andes Mountains, essentially.
Right.
And the reason for that is because you get a fantastic view of the southern hemisphere when you're down in Chile. There are other places, of course.
For those who don't know, the center of the galaxy is aimed at the southern hemisphere during most of the year.
Did I ever tell you a story about that?
No.
First time I ever seen the very center of our Milky Way directly overhead.
No, you didn't.
Okay, so here's the thing. Just to go down a little bit of a rabbit hole, with hopefully people will appreciate. So number one is if you go to a place to look at something in the sky, let's say the center of the Milky Way, and to find that, what you need to do, at least from the northern hemisphere, let's say tonight it's clear, is to look as soon as it gets dark, which is right around here is like midnight or something, right? You know, and then the sun is up by 2:30 or something, starts coming up, getting daylight again. But if you look directly towards the south, you're looking towards the constellation of Sagittarius. Mm-hmm. So the center of our Milky Way galaxies is in that constellation.
Right. If there's an asterism Sagittarius known as the teapot, and if you go just a little above the spout of the teapot, that's where the center is.
Yeah, and if you're familiar with the constellation Scorpius, so Antares is a very bright red giant. That's the kind of the eye of the constellation, if you like. That's kind of something to look out for, especially if you're an amateur astronomer. A lot of people like to peek in that area. But from the northern hemisphere where we are, right, so nearly 50 degrees north latitude.
Right.
The center of our Milky Way is really near the southern horizon, and that really gives you a crappy view, for lack of a better word, because of you're looking through more of the atmosphere.
You're looking through a lot of atmosphere
yeah,
at that point.
compared to when something's straight up above you.
Right.
That's sort of the minimum amount of atmosphere that you're going to look through. So to boil it down, essentially, if you want to get a good view of anything astronomical, hopefully you can arrange things such that it's directly overhead.
Right.
So if you want to get a good view of the very center of our galaxy, and what's at the very heart of the Milky Way, Robert?
Sagittarius A star,
And what's
or
inside
the
that?
supermassive black hole.
Yeah, supermassive black hole. So if you wanted to observe, let's say, stars that are orbiting that black hole, and get let's say, a precise measurement of the mass, because that affects the orbits of the stars around the black hole,
Right.
it's much better in terms of the precision of your measurements if the center of the galaxy is directly above you. And that is the case when you're in the southern hemisphere,
Right.
like in Chile. So what you want is a counterpart to this telescope, one in the southern hemisphere,
One in the northern.
one in the northern hemisphere. Now, there are a number of telescopes in the northern hemisphere, some of them on Mauna Kea in Hawaii, which is a really good place. Astronomers don't randomly put telescopes at different places on the Earth. They put them in different places where what we call the seeing is best, typically, if we're talking about like an optical telescope, for example. Of course, some telescopes, you can't even leave them on the Earth. Like an X-ray telescope, the X-rays get totally absorbed by the Earth's atmosphere. Those type of telescopes have to go in space.
Right.
But if you don't have the money to put your telescope in space and you need to build it on the ground, then you can be very selective on where you put it by watching the sky conditions over a period of time.
There's also a limit to how big of a telescope you can put into space, and unfortunately, to get higher resolution, you need a larger mirror, a larger objective. So there's trade-offs all around that have to be made.
And that's another important point for why Starship is so important. It's not just to get Elon Musk, etc., to Mars, if that's the case. It's also to put up things that are very big and large, like future space telescopes. And you can design them like the James Webb Space Telescope, which unfolds once it gets up there. So it has to be more compact to fit in the body of the rocket. But once, in space, of course, it can unfold. Think of it like an umbrella, for example.
Right.
That's kind of the idea. So if when technology advances to the point, we'll be putting up things, maybe 100 times larger than the collecting area of the James Webb Space Telescope. And the goal in optical astronomy is really two things. Number one, the larger the collecting surface, the more light you can gather per second, let's say, so you can see fainter.
Fainter objects.
And the other, of course, is that it improves the
resolution.
resolution.
The details you can see.
Exactly. And both properties are very important.
Yep.
So anyways, the LSST, which was the project that started the construction of what's called today the Vera Rubin Observatory, named after Vera Rubin. And we're going to say a little bit more about her later on, especially in the podcast, where we always give a quote.
Right.
And the quote today is from Vera Rubin.
Oh, cool.
And she was, no pun intended, instrumental in driving home the idea that there is sort of this underluminous material that's in our universe, matter that interacts with its surroundings via gravity, but doesn't really give off light. If it does give off light, it's very faint.
Okay.
And so what we discussed, now this was like back in like early 80s, late 70s type of thing. And Vera Rubin and colleagues did a lot of measurement of what we call the rotation curve of spiral galaxies, like Andromeda galaxy. The idea there, just to quickly give you, what's going on, is that the orbits of things in our galaxy, they're all orbiting the center of the Milky Way, ultimately, but those orbits are determined by the mass that lies interior to the orbit of the object itself. They're affected by the total mass.
And that's important too, interior, because exterior mass doesn't have any effect.
That's right, it gets canceled out.
It gets canceled out.
Now, you could think of the solar system as an analogy. The vast majority, 99+% of the mass of our solar system is in the sun. So when we look at the orbits of the planets like Mercury takes about 88 days to go around once.
Okay.
And it travels a lot faster in its orbit than comparing it to, let's say, Pluto, the dwarf planet, which takes about 248 years to go around once, and it's traveling a lot, even though the circumference is a lot greater, because its radius is a lot larger. It's 40 times the distance of the sun to the Earth, 40 AU. It's still traveling a lot slower in its orbit because it's much further away from the sun, and therefore gravity is much weaker.
Right.
Gravity falls off as 1 over the distance squared. So if you double the distance, the gravitational force is only 1/4 as strong before you did the doubling.
Right.
Now, the orbit of objects in galaxies and are affected by everything that's contained inside that orbit. And if you can get an estimate of all that stuff that's inside the orbit, and you do that by light, now that light could be in the form of optical light, or it could even be in the form of infrared or ultraviolet and so on, but we build detectors that can sense things that our eyes can't detect, can't see. And so we have a really good idea of the total amount of mass then that lies interior to the orbits of objects. And what we discovered was, through work like Vera Rubin, is that objects on the outskirts, especially of spiral galaxies, are traveling too fast in their orbit, as if there's a lot more matter inside of their orbits that we just can't see. It doesn't seem to give off any light. Right. Now, if it does give off light, it's very faint, intrinsically faint, and therefore very hard to detect. But all observations that have been done up to this point, since 1980, have shown us that this matter doesn't give off light at all.
Right. Now, I will bring up the point that these outer stars in the spiral galaxies are moving fast enough that, given the amount of mass we can see, they should be flying off into intergalactic space. They should be breaking away from the galaxy. They're moving that fast, that much faster than they should be.
Right. So Tony Tyson, who's like the principal scientist for the LSST project, which was the construction of the telescope, the Rubin Observatory, he likes to say that galaxy, or stars, I should say, in the outskirts of galaxies are traveling faster than the local speed limit.
Right.
That's how he likes to put it.
That's a good way of putting it. I like that.
Right.
It's simple and to the point.
So when you add up all of the matter that's required to have the orbits of stars going around the center of spiral galaxies that you actually observe, you find out that it's a lot greater than what you actually see from the matter that gives off light. So there's this matter there that doesn't produce any light. So the term that was used initially was, it was dark matter by Fritz Zwicky. He had discovered evidence for this in the 30s. As I said, Rubin and her colleagues, Kent Ford and others, discovered evidence for this in individual galaxies. So it was called missing mass at some point, but everybody now has settled on the original label that Zwicky gave it as dark matter. So it's matter. Why is it matter? Because it has gravity. It interacts with its surroundings, but it doesn't seem to give off light. Now, if it doesn't give off light, it probably does not have an electric charge. And that's from fundamental physics. Accelerating charges emit light. That's Maxwell, right? So if you're interested in that, look up about Maxwell's equations, if you want to get into detail about that. So it's some form of matter that has gravity, so it interacts via that force, but it doesn't interact any other way as far as we know. Or if it does, it's very, very type of weak interaction.
Right.
The problem now today is, what is this stuff? And that's one of the goals of this telescope and others too that we have, is to try to uncover the very nature of this dark matter.
Okay.
Now, as a betting scientist, the majority of that bet now is on the fact that it is some type of subatomic particle that we have never detected up to this point, because it's very elusive. It doesn't emit light. It only interacts gravity. Gravity's the weakest of all 4 fundamental forces.
So it takes a lot of stuff to have any real gravity.
If you fall off a ladder, you're going to probably hurt yourself. But why is that? Because you're being pulled down by all of the mass of the Earth.
Yeah. I like putting it this way. The next weakest force is the electromagnetic. Okay? So, people think, gravity's real strong here on Earth. Put a magnet on your refrigerator. Does it fall? No. Electromagnetism is so much greater that a little refrigerator magnet will stick to your refrigerator and resist all gravity of Earth.
And you can go even further. You could take like 2 electrons, let's say, and say, okay, what is the gravitational force of attraction? Because they have individual masses, separated by, let's say, 1 meter. and then compare it to the repulsion, because they're both negatively charged. They are repelling each other through the electromagnetic force.
Right.
And then look at the ratio of those forces, and you'll find the electromagnetic force is like 1 followed by somewhere like 48 or so, 47 zeros after it, stronger than the gravitational force. It's
Right.
not even in the same ballpark. It's so off, it's not even wrong, as some people would say. So it's like when you're dealing with subatomic scattering properties of particles, you never worry about gravity.
Right.
Never. That is the mass of the individual particles.
Your errors in your experiment are going to be much greater than the gravitational
It's just
effect.
completely negligible. I mean,
Yes.
you may as well just say it's zero, right? It just doesn't enter at all. But that's not the case if you have a lot of material. And so if you have a
Right.
lot of dark matter, even though it may be a subatomic particle, if there's like quadrillions and quadrillions of these things, then the combined gravitational attraction can add up to be something
quite
substantial.
significant. Right.
And definitely affect the orbit of objects in galaxies that we observe. So anyway, so that's a very interesting puzzle, and whoever discovers what dark matter is, there's a Nobel Prize.
There's a
waiting
Nobel
for you,
Prize,
right? And
hands
all that.
down.
Yeah, that's just like a major fundamental revolution and understanding of the very nature of the universe itself. If that doesn't get you excited, Robert, to want to take STEM classes and to be that person that figures it out.
That figures it out.
Look how
Yeah.
famous you would be. Rich and famous. Usually when you're famous, the richness will follow.
I mean,
right?
I'll even point out that if you prove that there is no dark matter, but it's some other fundamental force or something going on, there's still a Nobel Prize there. You know, whatever the answer is.
Yeah. So this observatory was initially built to do a complete all-sky survey in the south. Of course, they can't see the whole sky because
Right.
the Earth blocks the other half of the sky in the northern hemisphere. But it can do the southern hemisphere, all sky that it can see, so half the sky. And it was designed to take very fast observations using a very wide field camera. It's like 3.5 degrees or something. the
Something
field
like
of view
that, yeah.
of the camera, and it can take an image and then slew to the next position in slewing time is like 5 seconds.
Oh,
Start
wow.
to image. Now you don't have to slew it a lot, right?
Right.
Because you're just moving it a little bit and then take another image, then moving a little bit and take another image. You keep repeating that in a sort of jigsaw-like pattern, mosaic pattern, and then after 3 nights, you should cover the whole sky, and then you repeat that. So you take short exposures, but then you keep repeating those images, and what you do is, over time, you get multiple images of the same area of the sky, and you stack it together, would effectively give you a much longer exposure time. In other words, you could see fainter and fainter and fainter things this way. So that's kind of the basic principle behind the telescope and how at least it will operate for the first 10 years.
Because I will point out secondary purposes are this will spot minor planets, this will spot all sorts of things that are moving close by because you'll see them because of the high cadence moving.
Yeah, transient objects is one of the major
that's the
goals.
word.
Yeah.
Yeah.
So you can see things move. They were there one night, they weren't there a week later. Why?
Right. They moved.
They moved, right? Or maybe it blinked on and then blinked off, right? Because
Well,
we
that
know
would be
there's lots of variable sources out there.
Right.
So you could keep, track of all that kind of stuff from the near Earth environment, like satellites in space. You're going to see all that stuff.
To
All the way up.
supernova.
In fact, we had talked previously a little while ago that there is built. I guess we go down to. We already said stuff about it. It's public knowledge that there's built-in software that the observatory, if it observes a spy satellite from a certain country that doesn't want you to know its shape, put it that way, that data will be excised from the data before it's publicly released. So that's how good this telescope is. That government agencies around the world do not want this telescope to publicly release images of their equipment that they have in orbit around the Earth and elsewhere.
Right.
Interesting, but that is the case. So unfortunately, we won't see that type of stuff.
Because there were people that were ready to look.
Oh, you know it. In fact, if they're not 100% accurate, somebody's going to get that one that they missed, and that'll be all over the internet. You know that's going to happen. So people will be looking for things that were accidentally
Imaged.
and included in the public release of the data. That's the other thing. The National Science Foundation, I should say, put a lot of money into this project, and without them, of course, it wouldn't have come
Wouldn't
to
have been,
fruition.
yeah.
And that means it's public equipment when you think about it. In fact,
Right.
here at the university, right, if you go to get a grant to buy a microscope, that's not your microscope. You can't, when you retire, you can't take that home and put it on your shelf, right, and say that's mine. If it's purchased with public money, the taxpayer owns that equipment.
Right.
So that equipment is being, in some sense, leased to the university and then to you indirectly, right?
Right.
And so, so that's how it works, right? So this telescope is the public's telescope, and that's why this data is all going to be released.
Right. There's a period of exclusivity where the scientists that are
Yeah.
the PIs on it get to look at it, and then it's released to the public, so you can go mine it.
And the thing about this telescope is because you're taking so many images a night, you've got to go out and buy like literally hundreds of thousands of hard drives in order to store up all the data from this telescope over its 10-year lifetime.
Right.
And who has the capacity to do that, like individually, right? You're not going to waste your money, I don't think, on all those hard drives.
Right.
When you could build your own mansion or something with that
we're
money, right?
we're reaching the point where these experiments, these observations, are running into the petabytes of information.
It's going to be interesting to see. I know how the project itself, how scientists are dealing with the data set, and to be able to extract useful, let's say, gold nuggets out of the hay field, right? A hay bundle, right? I mean, haystack. I mean, that's the thing, needle in a haystack type of stuff. How are public citizen scientists, and I mean by that like amateur astronomers who are interested in grabbing the data, maybe doing their own thing, what kind of information are they going to be able to extract where they're not going to have really access to the full data set eventually?
Well,
it's just going to be too much data to handle.
And on that one, they'll be coding up their own pipelines to look for their specific type of object that they're interested in.
I wonder if that's out of hand though now because the data rate is so high. I mean, we used to, what's it like? The analogy everybody's heard. It's like drinking from a fire hose. You know what this is like? Drinking from Niagara Falls.
Yes. Yes. Oh, yeah. Any amateur or any actually, even the scientists, they're going to be looking at their one particular thing. They're not going to be looking through the whole data set.
I mean, if you dump all this data in the database, you don't want to say, okay, give me objects that are in this position of the sky that have these certain properties, and then you got to wait 10 years for the database, the computer that's handling the database to go through and give you those objects, right?
Right.
So time is of essence here. So it's, there's a lot of sort of work that's been done behind the scenes to speed up this whole process.
But this is part of why the data sets are released also, is so people who have the background and the knowledge can look at it without being professionals.
And the other thing too is this, because it's a survey telescope, at least that's what it's initially being used for, there are lots of other ground-based telescope or even space-based telescope like James Webb that someone will see a target of interest and then say, okay, we need detailed study in multiple wavelengths, X-rays, infrared, you name it, and train everything on that. Other individual telescopes, they'll of course go out and propose time to be able to use the telescopes to follow up some interesting object or objects.
Right.
Where this telescope, at least for the first 10 years or so, is going to be doing that survey. It's not going to be stopping and looking.
And I'll point to a couple of resources that do something with targets already like that. There's the Exoplanet Transit Database that looks for people who have the equipment and everything to go do follow-up observations of exoplanet transits. And you've got the American Association of Variable Star Observers, AAVSO, that look at variable stars.
And
they put out calls occasionally, hey, look at this target.
Yeah, they've been doing that for decades. In fact, that reminds me of a target that we've all been looking for a year now. Do you remember that?
T-Corabora.
T-Corabora was supposed to go nova last summer. It happens every 80 years on average, and the 80 years was up last year. So now if it goes this summer, it's 81, I guess. And it still hasn't gone off yet.
Nope.
In fact, it's in the Corona Borealis, which I had a great view of last week, Robert. When I was on vacation, I was away from the city lights. Right, I was out at about 1 o'clock in the morning on a clear night, and the Milky Way stretched from horizon to horizon. This is one of the best views I've ever seen of the sky for a long time. And Corabora was so there, right?
Right.
And you just count the number of stars, away going off one side there clockwise, right? Compared for where I was looking from. And that third star that you look at, it was just a single star. Beside it was no additional star.
Yeah. And it's one of those things where we're those people that instead of old man shakes fist at cloud, we're old man who shakes fist at stars.
Well, the thing is, this is prime viewing season, right?
For it. Yeah.
For if it goes off now, we'll all get a really good view with our telescope, assuming the weather cooperates.
Yep.
And so we'll see what happens. So hopefully this summer will be the summer for that. But that's just another example of some follow-up that you can do, right? You see, be able to track novae, right? Novae that no one had noticed because they're too faint. You're talking about 8-meter class telescopes. So if you get something that brightens up to only 20th magnitude, you're never going to see that in a small amateur telescope, and probably nobody would even notice it. You're going to be able to pick them up with this telescope.
Right.
You
and
see?
the pipeline will be looking specifically for that.
Yeah, and they're going to be looking for supernovae, and various galaxies, including our own, all kinds of stuff. I mean, I could see. Hopefully, we'll find a supernova in the Milky Way.
Yes.
So you know that we're well overdue for a supernova.
Yes.
I mean, we should. The last supernova that was visible in the Milky Way was over 400 years ago.
Right.
Talk about waiting around for something. Now, the argument is, if you look at other galaxies, it's much easier to see supernovae. Usually the dust is not in the way and get a better view of them. And from the statistics, you could say on average, maybe a supernova should go off in our Milky Way, one every 50 years or so, or one every 40 years. Therefore, there should have been about roughly 10 supernovae, exploding massive stars, or even the carbon detonation type from white dwarf. There should have been at least 10 of them in the last 400 years. Well, where are they? Well, the argument you can easily make is that they're far enough away that the interstellar matter, the dust, especially in the gas that lies between us and that supernovae, has dimmed the light so much so nobody recognized it. No one picked it up.
Right.
Maybe this telescope will finally be able to pick up some of those distant supernovae in our Milky Way. Wouldn't that be fantastic?
Some on the other side where all the center brightness and dark dust is in the way.
Now, I don't want one to go off nearby, of course.
Oh, absolutely not.
Betelgeuse would be just fine. That's about 500 light years away.
Right.
And if that goes off, they said it'd be so much light, at least when it reached peak brightness, you'd be able to read like a book or something at nighttime from the light from the supernovae.
I can't wait.
Now, our luck would be it would go off, let's say, in the summer, because right now that constellation is near the sun. The sun's
but
in
it
the
should still be visible in the daytime
It'll still be
sky.
visible, but it won't be as dramatic as
Oh,
what
no.
you would be if it was in the nighttime. You know what I'm saying here? If it waited that long, I mean, come on, right?
Yeah.
Anyways.
Give us a break here.
So there'll be a lot of interesting things that's going to happen with this telescope. Now, we mentioned the fact that it's about 8.4 meters in diameter. So the primary mirror, that's illustrated on the left side of the slide. The mirror is 8.4 meters in diameter, but the design is kind of interesting. So what you have, so typically, let's say a Cassegrain focus type of telescope. Now what that means is light comes down, let's say the tube of the telescope, reflects off the mirror that's in the bottom of the tube, gets reflected back up the telescope, and these mirrors are shaped usually like a parabola, parabolic mirrors as we call them. Then it hits off a second mirror, which is above the main mirror, and that's all supported by structure, so they're not going to fall into each other or whatever. And the light reflects off of that secondary mirror and then goes through the hole that's in the primary mirror. So it's like the primary mirror is like a donut.
Right.
And you lose some light. Why? Because there's a hole in the mirror, so it's not effectively a circle that has a radius of 4.2 meters, because the diameter is 8.4. And you say, okay, the surface area is pi r squared. Okay? In our house, by the way, pi we were round, but we won't get into
we won't get into that.
So pi r squared, you can easily calculate from the simple equation what is the surface area, which matters here. But in this design, there's also a third mirror, a tertiary mirror, but that third mirror is built in the primary, in the central region. So that effectively wipes out that area of the mirror, not just the hole, but also the surrounding area. And that's labeled here as M3 on this diagram that you can see there. If you take, then it gets reflected back from that third mirror effectively, off the secondary, which has some corrector plates, is what you're seeing on the right side there. And then the light ultimately then passes down through the center hole of the primary mirror. So this extra step. Now, the way they design that is such they want the tube, if you like, of the telescope to be as short as possible, because that makes the construction cheaper.
It also
Okay.
makes it where you can slew it faster because you're not putting torque and strain
Right.
on the tube.
And the other thing is there is effects in the light. If you take an image of a star that's near the center of the field of view, okay, and then you slew, that is, you move the telescope a little bit so that same object is near the edge of the image that you take with your camera, and then you look at the difference in the shape, you'll find they're not the same. So you get these optical effects that can occur. One's called spherical aberration. If the mirror is like the coma one is very prominent on objects near the edge of the frame. There are corrector plates that people can use and all this kind of stuff. But all that adds to the expense of it.
And it cuts down on each one absorbs a little bit of the light. Each one does its own little
let's say there's
anti-correction.
Right. So there are advantages and there are disadvantages for everything.
Right.
And you have to weigh them all out. So that's why they come up with this kind of unique design where you had this third mirror embedded in the primary mirror that would reflect back to the final not secondary mirror, but mirror that would direct the light back through the center of the primary mirror. So in other words, it's not just the hole that you cause light to be lost, but also this tertiary mirror.
Okay.
So then you calculate then what is the surface area that remains on the rim or the center. Like think of a donut, the center is missing, right? It's got a standard donut. What is left, the surface area of the stuff that you actually want to eat? You know, that part, right? And when you calculate that and then say, okay, what is the size of a perfect circle that I need to have that same surface area? Then that diameter of that circle is about 6.6 meters effectively.
Okay, so that's why they say 6.6 effective aperture. Okay.
So an 8.4 meter telescope effectively became a 6.6 meter telescope.
Okay.
And these sizes are always the diameters. That's how we...
I'm guessing, though, that the resolution will still be that of an 8.4 meter, but the brightness, the limiting magnitude, will be that of a 6.6.
Yeah, because you're getting stuff that are far apart on either side, signals, right?
And I'm pointing
Think of
that out.
interferometry.
Right.
Yes.
I'm pointing that out because the area that you're collecting light over is 6.6 meters, but the area that you're actually getting light to come in through is still 8.4.
Yes, and you could do that thought experiment by taking a big piece of cardboard cutout, cover the whole primary mirror, the whole thing, right? Cut out an area in the center so the light can get down through the hole of the mirror. But then on either side, just make a small circle about the size of an orange. And the light coming in those two small circles are separated by effectively 8.4 meters if you did it on the edge.
Right.
And so in resolution, it's just like you had that type of
8.4.
telescope. It's just that you're not going to see as faint because you only have light coming through a much smaller surface area.
I'm pretty sure that all this was thought through and thought
you
out
got
and
it.
planned on.
Oh yes, 100%. It's all related, to it. So it's quite interesting design of a telescope.
Absolutely.
And it's designed to be fast, which means take images and move on because you got to cover the whole sky in 3 nights.
Right.
So you can't fool around, right? You have to really go. And that's the primary selling point of this telescope. Now, you mentioned about asteroids. The first look images, which we're going to look at in a second, one of the images, first look at over 2,000 asteroids were found. Boom, bang,
Nice.
Already.
There we go. Proof of concept in the first light.
So how many hundreds of thousands ultimately will be found over the 10-year lifetime of this survey? And after 10 years, I don't know what the plans are for the telescope. I'd never heard, but you can imagine maybe we need to keep going. Let's put another 5 or 10 years, or maybe turn it into more of a pointing like targeting. But I think it's designed to be a survey telescope. Let's keep going. Let's find every asteroid that can potentially cause us a problem here on Earth.
Absolutely.
And you have to keep checking those asteroids. Why?
Because they're colliding, they're interfering with each other, they're getting close to other big bodies like the major planets.
They get heated up, remember?
They get heated up,
and so the
cooled
emitting
down.
of their light acts like little thrusters, so they're changing their orbits, right? Ever so slightly, but it all adds up over time. So you got to keep an eye on this stuff all the time. You can't just, do a complete survey and then say, okay, we're done. Let's go, I don't know, make a better airplane or something. You got to keep checking these things, right?
That's it.
So that, there's work, guaranteed work forever. If you want to survive or get a heads up of what's coming towards us.
Coming towards you.
Remember, the dinosaurs are not here because they didn't have a
space program or an astronomy program.
There you go. Space program would be better. Even if you had then you would know what's coming, right? And you couldn't do anything about it. I think having a space program and astronomy program.
That's the best. Yeah.
Would you want to know if you're in a dinosaur what's heading towards you, or would you kind of whatever, when it hits, it hits?
Yeah, I don't know. I don't know.
Okay, so let's look at some of these images.
Wow.
This is the image taken of the Virgo cluster of galaxies. That's the nearest cluster of galaxies to us. It's about 54 million light years away. It's part of a larger structure known as the local supercluster. And our local group, which includes both our galaxy, the Andromeda galaxy,
And about 20 others?
oh, more, hundreds,
Okay,
well,
100,
over 100
okay.
other ones. We found a lot more of these faint dwarf,
Faint
low
dwarf
mass galaxies.
Okay,
in
I
recent
didn't know
time.
how many of those had been
In
found.
fact, that's going to be another thing that people will be looking for. How many of
right.
these low mass galaxies that's near us that we've never seen because they're extremely faint? This telescope, looking over a large area, will be able to,
Will be
pick
find
up
them.
them with such a large mirror like that.
Yeah.
So that'll be interesting to see how those numbers change in the next, 10 years or so. So this is the nearest cluster of galaxy to us, and our local group is sort of on the edge of the local supercluster, where this cluster, the Virgo cluster of galaxy, lies at the
towards
very
the center.
center of
Yeah.
the local supercluster.
And I'm looking at this and I'm going, look at all those interacting galaxies. Look at all those.
I mean, if you
Wow.
the image is such that it doesn't do justice looking at it here. But if you take the image on your computer and then start zooming in on it,
Right.
the amount of objects, that's the other thing, right? You're going to need to categorize the position of these objects, measure their sizes, measure their brightnesses and multiple filters.
Their brightnesses, their profile of the brightness.
There are so many properties that you can measure the type of objects they are, whether they're stars or whether they're galaxies. And if they're galaxies, what type of galaxies.
Yeah.
There's all kinds of computer processing. Well, this type of telescope would be not useless, but not fully appreciated and utilized if we didn't have computers.
No. I hadn't thought about that, but yeah, without a computer to analyze this stuff,
You're going to lose a lot of information. Otherwise,
you're going to be looking at it going, ooh, pretty,
Yeah, move on to the next one, right? But yeah, there is a lot of work that's going to be done here. So we're in a target-rich environment for sure,
Right.
Data-rich analysis.
Wow.
Well, and that's why AI stepped in, right? AI has been used in astronomy since the 90s, believe it or not.
Right.
Convolution neural networks was used to classify different shapes of galaxies with training set. All of this stuff is not new to scientists and astronomers. It's AI stuff, right?
Right.
The buzzword.
It's a learning algorithm.
Yeah,
is
the
all it
general
is.
public hears all about deep learning, right? All machine learning, AI. It's all the same kind of ball of wax, right? It's just, generational increases in the technicality of the stuff, making it better and better and better. Now everybody knows about AI, of course.
Right.
It's one of these buzzwords that everyone likes to use. But AI is going to be applied to this kind of stuff because it just makes more efficient algorithms and hopefully faster to find things.
It's pattern seeking. I mean, if something's a repetitive pattern, it's perfect for finding it.
Yeah.
And so a lot of times that's what you're looking for, or disruption of a pattern.
And sometimes the patterns have multiple sort of things that affect them, right? Like multi-parameter space, as we would say. And it's hard to find those subtle patterns sometimes, or look at connections that otherwise you might miss. And AI helps with that, right? I mean,
Right.
they use AI for finding tumors, cancer tumors, and images taken of the body that otherwise maybe humans
would have
miss.
been missed.
So all of that is very useful, of course. So yeah, this image just demonstrates the power of this telescope. Number one, it works.
Yep.
Number two, you can get an idea of what is the quality of the images. It's very high, of course, very high.
Very high.
And it makes you excited. There's way more to come. This is just not even the cream on the top or the lick of an iceberg,
Yeah.
This is just a starting point. It's barely into it. So this is going to be really neat. And I got to use the word, I can't help it. It's going to be far out, Robert. How do you like that?
I like it. All right.
Next image, another part of the Virgo cluster. And then a Virgo cluster so big, can you look at it in one image and appreciate it? Everything would be so small you wouldn't be able to see it, right?
Right.
So you slice it up into sections. So
And
here's
zoom
another
in.
view. And you zoom in, and there's all kinds of stuff that you see going on in this image in terms
Look
of
at the
interaction.
tidal tails. Look
Yeah,
at
there's
the
shell-like
the
things.
jets.
There's jets coming out. All
Oh.
kinds of stuff that needs to explain. And a lot of this faint, look foggy-like stuff that you see here. There's intercluster medium and these tidal tails. A lot of that stuff, you need the larger telescope to see it in a
Right.
large area, right?
because this is dim.
Yeah.
I mean, this has a very low surface brightness.
Yes, that's the technical term. So if you took a very short exposure, you'd see the bright central region of the galaxies. You miss a lot of this interacting stuff that's out there.
Yeah.
So this is fantastic.
And I think intergalactic media, because a lot of this that's giving off light is actually heated gas. It's not stars like the galaxy.
Well, the
itself.
tidal tails would be stars that are torn out through gravitational interaction.
But
so
a lot of that diffuse glow is probably media, isn't it? Just gas?
no, most of the gas in clusters like that is hot, and you see it in X-rays. You don't see it in optical
You wouldn't
light.
see it in optical. Okay.
Yeah, not as much. You can, but what you're seeing here, these tails, that's material that's being drawn out through gravitational interaction as galaxies move past each other and draw out their material. So you're going to get a lot of information, number one, about dynamics, the movement of these galaxies and how they're related to each other and their positions and so on. You get a lot of information then about the structure of this cluster. And that ties into dark matter.
Right.
Because the total amount of mass that's in this cluster is not just what you see in the light, like you see here in this image. It's also a huge component is this dark matter. And all of that weighs in, no pun intended, of the effects that you're going to be able to see. Yeah. And so some of the analysis going to be done is, can we get a better handle on the dark matter and how it's distributed, and maybe ultimately tell us more about what it really is in terms of the fundamental properties by looking at what you see in visible and other forms of light, multi-wavelength light.
I mean, people be scanning this from Einstein rings and things like that that'll give clues to all of that.
Yeah, and you can measure the colors of the lights. There's all kinds of stuff that you can do here. Very, very, very interesting stuff. This image is of a star formation region, actually one huge one that's connected, as you see here. Yeah. And what you have sort of at the top off to the right is the Trifid Nebula. That's a classic, amateur astronomer type of on your bucket list.
Several good images of it myself.
You want to see. And then near the sort of center in the lower part is the Lagoon Nebula, which is spread out more. They're both about roughly a couple thousand light years away from us. But it's all connected. It's one giant star formation factory. You see? So you don't appreciate, you think these isolated individual targets that you normally would see, and you don't realize that they're actually intimately connected. If you look in the right way at faint connections, right, you see the connecting bridges of material. So it's really cool in that sense.
The cloud of it around them,
So if you want to understand how these giant molecular clouds form to begin with, what about the details of star formation? This will point the way. This will map out over large scale the distribution of the star-forming interstellar matter that you see everywhere, and then lead to different insights into how stars form, giving you maybe targets that you then can analyze in detail with other instruments.
Absolutely. I mean, this is the type of stuff personally I'm interested in because, the other stuff I wow at and I'm familiar with it and what you can do with it, but star forming and planet forming is what I trained for.
Yeah.
And so these regions are just amazing and wow.
I mean, I was part of the LSST science book that was published a few years ago that you can get. And if I remember, it's well over 1,000 pages of all the different science goals that you can attack with a telescope in a project like this.
Absolutely.
It's just everything, like I said, from the really near space environment of the Earth all the way out to the edge of the universe. And everything in between. Exciting times ahead.
Exciting times. Then there's this.
What's that? That looks like a fishing net. How did that get in that collection?
It looks like when I get backlash in my fishing reel. That's what that looks like.
This is like a fly net when you're in a heavily populated area of mosquitoes or something, right? Now, of course, the telescope is on the ground, and one of the things you need to see the universe is to look through all of that space that's near the Earth. And what's in orbit around the Earth? And lots of them, Robert, of course.
Lots of them. Satellites.
Lots of satellites. And in fact, I remember when I was really young, we used to go outside in the dark and look up, and you could track the satellites.
Yes.
And especially just after the sun went down and just before it rises, in the morning, you could eat because the alignment, the geometry is right that the sunlight reflects off the surface of the satellite and then back down towards the Earth. So the satellite is in sunshine where you on the Earth are in darkness. So it made it a little easier to see. Now you have no trouble seeing satellites. In fact, going out, as I mentioned when I was on vacation, going outside, I've seen them all the time. You don't have to even look for them. They're just there, moving targets.
Right.
There's so many satellites and in fact, people are starting to worry about the fact that after a while, there's going to be so many satellites in orbit around the Earth that there's the chance of collision between satellites is going to become high. So high, in fact, and then those collisions, you produce a lot of debris that essentially you're going to make the space above the Earth a very hazardous environment in order to go through, let's say to go to the moon or onto Mars or some other planet. You have to pass through that debris field that would be orbiting the Earth. And if that debris field gets dense enough, it becomes you can't even get through without getting, and this stuff is moving at 5 miles a second. So you can imagine being impacted by a lug wrench at 5 miles a second, and you're in your spacecraft. You don't want to take that type of an impact, obviously.
No.
So this is an image that was taken by Peter Brown and his group at the University of Western Ontario. That's the old name now. It's Western University. And basically they look at this. They look at a lot of studies with meteorites and tracking where they land and try to find them and stuff. But this is, so they take that system that they already had work looking at an idea of what the number of now satellites in space have increased dramatically over the last several years due to Starlink and other things like that, where obviously SpaceX is putting up all kinds of these small satellites.
Right.
And continuously, essentially, right? So this is an image taken of the sky back in February 22nd of this year from 14 different cameras, right? And you can see the crisscrossing path. When the satellites move across, as you're taking an image, you'll get this bright streak because of the reflected sunlight.
Yep.
And you see that in almost any image. In fact, the LSST project using the Rubin Observatory, that's one of the major sort of punch in the guts that was taken a couple of years ago when we realized how many of these satellites that SpaceX and other companies were going to be putting in space. That any of these large images over a large field of view, you're going to have streaks all over the place. And how do you get rid of them? They're going to spoil the images. So you can do sophisticated analysis. In fact, this was a problem when I was collecting data from telescopes for my PhD thesis. Occasionally, you're going to see satellites going through.
Well, and that was the thing. Occasionally, you'd see them.
And so what you would do, you'd accumulate enough images that you would just mask out those pixels that had the satellite trail.
Right.
And then when you stacked images together, combine them in the computer would reject those bright pixels. And so it was as if the satellite never went across your image.
Right.
Now you got to do that. You're going to have all kinds of, so it's a real challenge, and it's only going to get worse, right? Because people are proposing, all different countries have their own systems they're proposing, putting together, and so
the Rubin telescope I'm going to imagine with a 3.5 degree field of view, there's probably several satellites in every frame.
Oh, guaranteed. There's going to be a ton. In fact, they've done experiments with that.
Okay.
So we have an idea. And in fact, the images that were released here have been cleaned up. You don't see any satellite trails. They've been cleaned up. But you have to take multiple exposures in order to
know what's
stack
there
them together.
when the satellite is there.
So every single precise location of the sky, you want to take an image of it at least once when there's no satellite passing through.
Right.
And then you take all those pieces of the sky that have been no satellites passing through and stack them together in a single image. That's essentially what you're doing with the computer. So it's a lot more processing that needs to be done than otherwise would have been.
Right.
But what do you do? Advancement of technology? I mean, is that what this is? To a point? But anyways, we'll see how the future goes there. But this gives, hopefully, people an idea how many satellites are in Earth orbit.
When we're complaining about satellites interfering, this is what we're talking about.
Now, some people would say, okay, well, then don't put your telescopes on the ground. Put them in space. That's where they should be. You don't have to worry about the atmosphere, yada, yada, yada. That's nice, but where's the moolah?
Where's the money coming
Because
from?
it's going to cost a heck of a lot of money to put something like the Rubin Observatory in space.
Right.
I mean, it cost a lot. What was the price of the James Webb Space Telescope? Like $10 billion?
Yeah.
And you're looking at roughly the same cost for a Rubin Observatory.
Right.
So where's this $10 billion coming from when most people don't have that money? Even governments lack money nowadays, right?
Right.
Running deficits up to you know what, right? So
there you go.
There's always going to be a problem with that. So that's something humankind will have to address this issue in the near future. Now, some other news that I wanted to make a point of addressing is that the European Space Agency, ESA, has started construction on LISA. ESA on LISA. Now, LISA stands for, and you can see it written there on the slide, Laser Interferometer Space Antenna. It's a gravitational wave detector. In fact, it was proposed many, 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 many years ago while scientists were putting together things like the gravitational detector LIGO and others here on the ground. Now, our first gravitational wave was detected back in September, I think it was, of 2015. But prior to that time, it was just theoretical. This is a prediction from Einstein's general theory of relativity that any accelerating mass that's sort of asymmetric,
Right.
so think of a dumbbell, but the weights are unequal on both ends. If it's spinning around, it will generate gravitational waves. And the gravitational wave you can think of it as undulations in the fabric of space-time, if you want to think of it from a romantic point of view. Right? And people have written articles and books with those titles type of stuff.
It's a much more complicated picture.
It's much more
complex.
It's really a stretching out and a squeezing together in different orthogonal or directions of space itself. Now, these sources that produce gravitational waves are luckily very far away. You don't want a source producing gravitational waves near the Earth because it could literally stretch out the Earth by hundreds of meters in one direction at the same time squeezing it at 90-degree direction.
Yeah.
That would cause dramatic earthquakes and destruction of life here on Earth. We don't want that.
We don't want it.
Now, these gravitational waves, they get weaker with distance. They fall off as one over the distance.
Mm-hmm.
And most of these sources, thankfully, are millions, if not billions of light years away. So by the time the ripples reach us, they're very, very, very subtle. It's like you're sleeping on a boat in the middle of a calm lake, and somebody on the other shore a mile away tosses a pebble in the water. A young child is playing. And those ripples spread out concentrically from the point of impact of that rock. And eventually that disturbance will reach you on that boat. But by the time it reaches you, the amplitude, the height of the wave is so minute, you may not even be able to detect it.
Right.
Now, for these type of sources, on average, by the time the gravitational wave reaches the Earth, the amount of stretching and squeezing of space is smaller than the nucleus of an atom, which makes it extremely difficult to detect. And the basic process of detection is using interferometry, the interference of light. You can have light, let's say, travel down a path, a straight line. You can use lasers, of course, and you can have it go down a tube that's evacuated so no air is in the way or affecting the experiment, reflect off a mirror, and then come back to your source. And you got, at the same time, you can have a laser, going down another length of tube that's at 90 degrees at right angles, reflect off the mirror and come back. And if you adjust the distance from the source of the light to the mirror in either leg, either tube, in the right precise way, you can have the wave combine in such a wave that it destructively interferes. So when one wave coming from down one leg reaches a peak, the other one reaches the trough. And when you add those waves together, you get zero if it's perfect destructive interference.
Right.
Now, along comes a gravitational wave, slightly alters the length of these tubes in such a way that for a brief period of time, the light is not perfectly destructive interference. So therefore you see light when you shouldn't. And you can have a computer sitting there watching with a light sensor, reporting when it sees light. But of course, with these ground-based instruments, you got to worry about things that are not gravitational waves, like the shaking of the ground due to normal earth tremors or earthquakes, the shaking of the ground due to the passage of an 18-wheeler on a nearby interstate, the shaking of the ground due to a tornado that's a few miles away. All these different, the pecking of a bird on the side of the instrument has been shown to produce false signatures.
I've heard that this, not gravitational wave, but a light interferometer in Australia was dubbed the greatest kangaroo detector in the world, because the kangaroos hopping by would
set off the
detector.
Any type of earthly interference then is going to cause an issue. And the detection that was made first, and we've had hundreds of detections since then in 2015, was because the engineering got so good they could isolate the mirrors then from the shaking of the Earth. And eventually you get to the point where just thermal and quantum fluctuations will disturb things. Well, before we reached that point in 2015, before the engineering got good enough for the isolation of the mirrors and the equipment, scientists were already thinking maybe we shouldn't even worry about having this stuff on Earth. Let's put everything in space. You don't have to worry about shaking of the Earth.
Right.
So people had different designs. One of them was the LISA design that we're showing here. Now, there wasn't, in my opinion, it didn't seem to be a lot of work going on. The project cost a lot of money, of course, but it seemed like they were dragging it out because you weren't 100% sure that gravitational waves even existed. Number one, it's theoretical. Nobody ever detected them before. Yet, it's a prediction from Einstein's general theory of relativity, and scientists love predictions to be wrong because that tells you something new, right?
Tells you something new. That's job security proving things wrong.
So we didn't know for sure. So why are you going to spend all this money? Well, thankfully, scientists in the United States convinced the National Science Foundation to spend hundreds of millions of dollars to build the ground-based detector, and ultimately the detection was made.
Right.
Now, since that time, I think then we realized that, hey, we can do a better job at detection of gravitational waves coming from things like merging black holes, neutron stars merging, neutron stars and black holes merging, all kinds of things. Supernova explosions ultimately would release gravitational waves. In fact, the beginning of the universe
would release gravitational
waves.
waves.
Primordial gravitational waves. Whether or not we can detect them with our instruments, we'll see. But that's something we need to look at, and people have been looking at that for a long time now.
That makes me ask a question that I'm going to ask you about after the show.
Okay. But the thing about gravitational waves is that if they're produced from the Big Bang, they would come out immediately. There's nothing holding them back.
Right.
Unlike optical light, which is trapped by the ionized material for 380,000 years before it can come out. Neutrinos, they're released in the first second, but gravitational waves come out instantaneously. Boom.
Right.
So that's the earliest you can probe back to the very earliest moments of the beginning of our universe as we know it. Now, the thing with LISA, though, because you're in space, then you can have these arms that we talked about where lasers would go down these various arms. And in this design, as you can see, it's shaped like a triangle. These arms can be very long because the spacecraft are separated from each other in essentially the vacuum of space. In fact, the present design has it as the separations or the sides of the triangle, if you like, are 2.5 million kilometers.
Yeah.
So you have lasers shooting from all three stations towards each other.
So that'll be some very low amplitude gravitational waves that it could pick up.
There you go. Things that you couldn't detect here on Earth.
Right.
And there's the advantage of there. So this whole thing, they started building on it. So like I said, there's more of an emphasis to get this done. So the construction has begun, and launch is expected in 2035, so about 10 years from now.
Okay.
And there's always delays in this stuff. That's another reason why you should eat healthy.
And then it'll
so
be
you
a
can
few
around.
years getting them in position.
Yeah, so that whole food plant-based diet, Robert, that we talked about,
yeah.
you got to get on that, man. You got to get on it. You want to be here to see the results of this stuff. We got to do a podcast when the results first come out.
There you
and
go.
the orbit is an Earth-trailing orbit to get away from the interference of the Earth at roughly, a semi-major axis, an average distance from the sun about 1 AU.
Okay.
So it's not going into one of these L1, L2 positions or anything like that, right? And it makes sense because look at this side lengths that you need here, right?
Right.
And there's so much other stuff in those positions that would just interfere, right?
Absolutely.
So you got to keep away from that stuff. And the final thing we're going to talk about today, of course, it is now for us in the Northern Hemisphere, it is now
Summer.
I don't know if you caught it, but on the summer solstice, when the sun rises for the first day of summer in England, everybody gathers around Stonehenge. Mm-hmm. And the English Heritage, they broadcast this live on YouTube. And I caught it this year as well. The time difference
I didn't.
The time difference from where I was, it happened, sunrise was about 12:51 a.m.
Okay.
And I was still up. And by the time the sun actually gets up over the nearby hills, it was probably about 10 or 15 minutes after the hour type of thing. You had to wait a little longer to see the sun. And I was at Stonehenge a couple of years ago, and the thing, I was there in March during spring break. You can't get up to it and touch or lick the rocks or something, right? You used to, right? But people, I think they got out little knives and started carving away some of the stone, and eventually it would be nothing left if people kept doing that, right?
Right.
So they had to put like a fence essentially around like a thing that you can move. Like it's like a construction plastic fence that they have, a temporary structure, and they remove that for the summer solstice, so you can actually, that's the time of the year you can go right up to the rocks and hug them and get pictures and touch the rocks. And I mean, you're looking at something, these rocks, the oldest ones were put there 5,000 years ago.
Yeah.
And you can imagine, this is in England, right? The Romans, right, coming in like Caesar, right, coming into England and eventually getting to this place and looking at the structure and wondering who the heck made it. And number one, why did they put these rocks like they did? Went through all. And so it's quite interesting. And to get into a little detail, it's a cemetery place. It's a place where people had buried people.
Right.
So we think that at least the modern view then is this a place where people were buried, and then the taller rocks you see there were actually put there later on. So not everything was put down at the same time, type of thing. It was spread over many years.
Many years, yeah.
Yeah, but it's really interesting, and if you ever get a chance to go to Stonehenge, don't pass it by. It's really kind of cool.
Cool.
And of course, they always say there's alignment if you get on your knees and look through the right way at this angle. Just look at the sun go on the first day of summer goes through, and you can see whatever, right? But anyways, it's still interesting. And the way I think about it is every time I see people gathered there, it means it's the first day of summer for us.
Right.
And I enjoy it given the fact we have harsh winters around here.
Oh, yeah.
Well, not super harsh, but summer is certainly better. I like summer better than winter, we'll put it that way.
I don't, but I don't like the deep depth of winter here either. So
yeah, there's goes from one extreme to the other.
The other, yeah.
But if you want to learn more about everything we talked about today, of course, one of the things you can do is you can take higher education courses in any field. Yeah. In fact, if you're interested in English, it'd be nice to report on things like the Rubin Observatory is going to look at and the significance, why it was worth the money to build in the first place. All of this stuff needs to be communicated to everybody.
Right.
So
big
shout out for English.
So we advocate for the sciences, but in reality, we advocate for education in general. So.
Well, scientists have to write papers.
Absolutely.
We need to communicate. And if you can't communicate, you can't do science.
You can't do science.
Not modern science anyways. So it's extremely important. And if you want to take those type of classes, of course, come to the University of North Dakota. We have a lot of online classes that you can take. We also have a lot on campus, so you can come and join us. And if you're around, feel free to drop in and see Robert and I.
Absolutely.
Now, our next podcast will be July the 1st, which is Canada Day.
Woo!
Even though I was born in Canada, I still will be here to do the podcast.
All right.
Maybe I'll wear some merch or something from Canada while I'm here.
Some maple leaf and bring some syrup or something.
Yeah.
Sorry.
We'll see how that plays.
Sorry to our Canadian audience.
Now, we always leave you with a quote, as I alluded to at the beginning of the podcast. Today's quote is from Vera Rubin. By the way, she passed away back in 2016, so she hasn't been with us for a while now, 9 years. And the quote is a description about dark matter. Remember, she was one of the primary discoverers of dark matter. So her quote is, "I wonder if the explanation," and this is of dark matter, "is even more complex than we imagine at present."
It always is, folks.
Yeah, so
it
with
always
that,
is.
Thank you very much for viewing. Give us a thumbs up if you like this podcast. Subscribe if you haven't subscribed. Tell all your friends.
And show up next week.
View the Cosmic Pie podcast because we love seeing you here.
Absolutely.
See you later. Thank you.
Bye, folks.